Let's talk about how to solve the problem. So we know that average values of your sample are random values which are normally distributed around average value a population. But we know, on the other hand, that to use this knowledge, we also need to know the standard deviation of your population, which we never know. So what we can do? Let's start with some reflections. So we know that we need to know sigma. We don't know it. But on the other hand, we can estimate sigma by computing standard deviation of your sample, S. However, apparently, like m is not equal to mu, S will also not be equal to sigma. But we know that it will be somewhere around, so we kind of introduce additional uncertainty if we use S instead of sigma. And we also know that the larger sample size is, the smaller uncertainty is. And therefore, for large sample size, the difference between S and sigma will be quite small. However, for small sample size, this difference can be large, and therefore this uncertainty will depend on the sample size. This additional uncertainty will depend on the sample size. It means that we need a distribution which will let us using S instead of sigma. So in normal distribution, we cannot use S instead of sigma. We need to use sigma. However, we need a new distribution, which will be like a new version of normal distribution, specifically designed for small sample size, which let us use S instead of sigma. However, this distribution should penalize us. What means penalize? It means it should kind of introduce additional uncertainty, so the intervals should be bigger if we use S instead of sigma. And this penalty should depend on the sample size. So these are the general ideas. So we need to modify normal distribution, so it means we need to create a new distribution which will be similar to normal, however will have this additional uncertainty parameter, right? So, and when sample size is small, then the error margin will be larger than the error margin that we have here, right? So if we use ZS instead of sigma, this error margin for small sample size should be larger than this error margin. But the bigger sample size is, the closer and closer and closer this error margin should be to the one that we use for in case of normal distribution, right? So this distribution is known as students' t-distribution. Why students? Because actually it was designed by William Gossett, who worked for Guinness Factory. He was educated as chemist and mathematician, and he worked on optimization of beer brewing process. And of course, when you optimize a large production process, you don't have a possibility to run it hundreds of times, right? Because it will be too expensive. So he designed this distribution which aims at approximate normal distribution for small sample size. However, he published all his scientific papers with using the student pseudonym, and therefore we know this distribution as students' t-distribution, not Gossett's t-distribution. So let's recall first that standardized normal distribution is bell-shaped. The average of standardized normal distribution is 0. The standard deviation equal to 1. If you want to get an interval, for example, of 90% of most common values or 95% of most common values and so on and so forth, we should take Z standard deviations around mean in case of the standardized normal distribution is just Z, right? For example, for 95% cases, Z equal to 196, and it's fixed. Z score, how many standard deviations we should go from the mean, it depends only on this percentage or probability value, right? This is an example. If we have normal distribution, if we want to have 95% interval, we need to take 196 standard deviations on both sides of the mean, or if it's a standardized distribution, we simply go from 0 to plus 196 and to minus 196. So that's what we know about normal distribution. Now, students' t-distribution, it's also bell-shaped. It also has average 0 and standard deviation equal to 1. However, and here is the difference, for any interval, for example, for 90 or 95% interval, we take not Z, but T standard deviations. So we have a new score, T score instead of Z score. And Z score, you remember, it depends only on this, how big the interval is in terms of probability or percentage, but T score depends on two things. It also depends on this probability or percentage, but it also depends on the other thing, which is called degrees of freedom. And you remember what is degrees of freedom? It's a number of independent values you have. For example, if you want to get the same interval like here, 95% interval, and if your sample size is 3, it gives you 2 degrees of freedom for distances. You remember when we compute variance, it's always n-1 because we use 1 degree of freedom to compute sample mean first, right? Then the t-score will be 4.3. So it will be more than 2 times larger comparing to z-score. That's exactly the penalty, so the interval will be wider. This is t-distribution for 2 degrees of freedom. And then you can see that if you want to get 95% like this, you should take 4.3 and minus 4.3 standard deviations. Or if you talk about average value standard errors, right? So that's the main difference. So in t-distribution, we use, instead of z-score, we use t-score. And t-score depends on 2 things. It depends on the probability and it depends also on your sample size. Another example, if I want to get, again, 95% interval, but I have a larger sample size, for example, my sample size is 10, it gives me 9 degrees of freedom. And look, instead of 4.3, my t-score is getting smaller. Now it's 2.26. So in this case, interval will be closer to this one, although still larger, because here we should take 2.26 standard errors away or standard deviations away from the mean, while here it's 196, right? And then you can assume that the bigger sample size is, the closer and closer and closer this value will be to this value. For example, if you have sample size of 100, so it gives you 99 degrees of freedom. In this case, the t-score will be 198, although it's just a little bit larger than 196, which we have in normal distribution. So when your sample size is really, really large, then the t-distribution converges to normal distribution. But if sample size is small, then it will be simply wider, so it gives you additional uncertainty. Okay. So this is just an example. Here I have all 3 cases. You can see sample size is 4, sample size is 10, sample size is 100. And then you can see that the curves that show the distribution, but the bell shape, they are a little bit different. And therefore the interval for 95% is also different. So this is the widest interval you can see, right? This is for the case n equal to 4. This is the next biggest interval, which is for n equal to 10. Then you can see this is the interval for n equal to 100. So it gets smaller and smaller and smaller until it reaches this one, 196 exactly. Okay. This is just an example also, just another view to these curves, a little bit bigger so you can clearly see the difference. So t-distribution let you, first of all, use small sample size. Actually, you can start with sample size of 3 or 4, and then it will let you use standard deviation of your sample instead of standard deviation of your population, but it will penalize you by giving you larger confidence interval. So the confidence interval will be larger because the t-score, which is actually responsible for these intervals, and the shape of the distribution will be also dependent on the sample size. Okay. So this some takeaways, main takeaways. So students t-distribution, it's an approximation of normal distribution for small samples. It depends, if you talk about standardized distribution, it depends only on one parameter, it's degrees of freedom. In case when you use students t-distribution for computing confidence interval for average values, then degrees of freedom it's n-1. The expected value is 0, the variance is 1. And then when degrees of freedom is very large, then this distribution will be almost identical to normal distribution. As usual, R has all main functions for this distribution. You remember that the function starts with letters R, D, P, and Q. R for random values, D for density, P for probability, and Q for quantiles. And then you just add name of the distribution, which is in this case just t-distribution. So you can get random values from t-distribution, you can compute density for any value, you can compute probability for any value, probability to get a value smaller than given, and also compute quantiles, exactly like we did for normal distribution and for uniform distribution. This is a table, so you can also find tables with different t-scores. For example, if we talk about 95% interval, you can see that if this is degrees of freedom, so remember it's n minus 1. For example, if you take this one, you can see it's for degrees of freedom equal to 1. It means it's n is equal to 2, right? You can see it's 12. So instead of 196, we have 12. So if you have a sample size of 2, I would never use sample size of 2, of course. But theoretically you can, but in this case the penalty will be huge. And then if you switch to sample size of 3, which is 2 degrees of freedom, you remember this is 4.3. We also discussed the situation previously. So this is much smaller, right? And then you can see that this is the 9 degrees of freedom. So this is the sample size of 10, and then so on and so forth. So this is just an example to compare different t-scores for different sample size, right? And then if you have sample size of 30, 29 degrees of freedom, the t-score will be approximately 2, and then it will be 198 if you have approximately 100. And then, of course, when you have infinite, then it will be the same as the normal distribution z-score. Okay. And this is just an example how to check this. So you don't need these tables, actually, although you can still find them. You can just use the Q function for t-distribution. And then you remember, for example, for 95% of the cases, you remember you have 95 in between, 0.95, right? That means that 5% outside, 2.5 here, 0.025, and then 2.5 here. So this area will be 0.975. So this is why, for example, this t-score can be computed like this. For 975, probability to get smaller value, right? So it's 2.04. And then for this t-score can be computed for this one because this area exactly 0.025. And then it's minus 2.04. Because t-distribution is also absolutely symmetric, you can compute just one of those and then use plus minus in this case. So that simplifies calculations a little bit. Okay. So this is it. Now let's kind of make a conclusion. So average of your sample is distributed normally. Standard deviation of this distribution, which we call standard error, it's sigma over square root of n, where sigma it's a standard deviation of your population values and n it's your sample size. And then this is how we write it mathematically. And then you remember z-score, it depends on the confidence level, right? If your confidence level is 95%, z-score is 196. If your confidence level is, I don't know, 99.7%, then the z-score will be 3. Okay. However, in reality, we can approximate normal distribution using t-distribution if your sample size is small. In this case, you will be allowed to use S instead of sigma, so you can use sample standard deviation instead of the population standard deviation, but that gives you the additional penalty. And you can see that the expressions, they look very similar instead of these ones. Here we use z-score, here we use t-score, and you remember that the main difference between z-score and t-score is that t-score depends on both confidence level and degrees of freedom, which is related to sample size, right? So t-score depends also on sample size. The t-score, the smaller sample size is the larger t-score. Okay. Now, finally, we can solve the initial problem I started this learning sequence with, how to compute confidence interval for the average sugar content in the whole tree or in the whole garden if you want. Now we have everything we need. We will use t-distribution instead of normal distribution because in this case we don't know the population average, population standard deviation, right? So again, we use R. So first of all, I combined all these values that I measured for 5 apples taken randomly from my population. I compute the size of the sample, it's just the length of this vector, it's 5. I compute the average sugar content, standard deviation, and now I compute standard error by taking standard deviation of my sample and divide to square root of sample size. So this is my standard error, right? Now I can get the t-scores for left and right tails. So for left tail, I computed for probability 0.025. It gives me minus 2.78. So this is the t-score for 4 degrees of freedom. Because I have sample size is 5, it's 4 degrees of freedom. I compute t-score for the right tail. You can see, or for the right boundary, I use probability of 975. So you can see the in between, I have exactly 0.95. And then you can see it's the same, but just it's a positive instead of negative. And then I can compute it, for example, I can compute error margin by taking the positive t-score by just computing t times standard error. It's exactly what I have here. It's 0.56. So this is the distance between m and mu. So this is maximum distance between m and mu we can expect in 95% of the cases. Or in reality, it's our estimate for this distance, right, using t-distribution. So we know that in 95% of the cases, it will not exceed 0.56. Now, we can use this distance to compute confidence interval. So we have m, we take m plus error margin, we take m minus error margin, right? And then with a given chance, the mu will be inside, or in the correct way, to say this in the correct way, we had 95% chance before we took a sample, we had 95% chance to get the real mu inside. Or if you repeat this many, many times, then 95% of your samples will have mu inside the corresponding confidence intervals, right? So this is my confidence interval, this is the lower boundary, this is the upper boundary, and now I can write it like this. So the question is, how sweet the apples are in the whole population, how much of sugar in average they have in the whole population and the whole garden. And my answer will be between approximately 9 and 10 grams per 100 gram of apple mass or weight %. So we don't know exactly, somewhere in between with 95% confidence. So we still have a possibility that it's beyond this interval. Okay. You can also compute it easier to avoid all these manual calculations. There is a special function which is called a t-test. Actually, it's a test, but it also computes confidence intervals. We will discuss test in the next learning sequence. So if you write t-test and then provide your sample, the values of your sample x, then you will get a lot of information, but most important information stays here, 95% confidence interval, and then you can see that we got almost identical. You can see here we have 894 and 10.06, but if you round these two values, you will get the same, 894 and 10.06, despite that we rounded some of the values, right? So our calculations were quite precise. You can also compute it for another confidence level. You know how to do it manually already, but you can also do it using t-test. You just need to provide extra argument, confidence level, and that's, for example, the confidence interval for 99% confidence. So in this case, 99% of the samples, if you compute it with 99% confidence, will contain the true mu inside. So before we took our sample, we had 99% chance to get it inside. So this is, we are pretty confident that the true mu is inside this interval. So we have a good estimate of the true mu, right? So this is it. Now you know how to compute confidence intervals for average values for your population based on the statistics of your sample. We use t-distribution for that. Then I have a Grasta app, which also shows you how it's calculated. So you can take a lot of samples. For example, you can indeed take 100 samples and see how many samples have the true mu inside the confidence intervals. The next video, I'll tell you how to use this Grasta app, and then come back and we will discuss how to do the same things, but for computing confidence interval for variance and standard deviation.